Hello friends, welcome to engineering tutorial. So we have already discussed some basic concepts related to electrical machines, electromechanical energy conversion, basic electromechanical devices, and in general the continuous energy conversion devices or rotating electrical machines. So in this video we are going to discuss about the fundamental principles, the laws that govern the operation of electrical machines, essentially the rotating electrical machines, that is motors and generators. So the rotating electrical machines, we have already discussed that it essentially involves conversion of electrical energy into mechanical energy. So it involves an electrical system, a mechanical system on the two extremes with a coupling magnetic field. So the electrical parameters that are involved are obviously voltage or current, and the mechanical parameters that are involved are torque and angular speed. So the magnetic field will also involve parameters such as magnetic flux density, etc. So the fundamental laws that govern the operation of these rotating electrical machines will basically be the electromagnetic laws, because there is a magnetization of a conductor that is going on in between this electromechanical energy conversion. So it will involve the voltage, current, the electrical parameters, the mechanical movement, torque, angular speed, the mechanical output, and the coupling magnetic field, which will involve magnetic flux and magnetic flux density. So the operation of all rotating electrical machines can be summarized together and can be explained on the basis of two fundamental electromagnetic laws. First one is Faraday's law, and the second one is Maxwell's law. Okay, first let us discuss Faraday's law. So according to Faraday's law, it states that when the magnetic flux, that is a conductor which is placed in a magnetic field, okay, a conductor which is placed in a magnetic field, let's say we have a coil, this coil is placed in the magnetic field produced by this magnet, okay. When this magnetic flux fluctuates or changes, because the magnetic field is not uniform, it is not same everywhere, so when it fluctuates or changes, there will be an EMF induced in this coil, across this coil, okay. So whenever the magnetic field or the flux associated with this coil, it will change, it will fluctuate, there will be a voltage, an EMF that will be induced across it. So the magnitude of that EMF is given by the mathematical expression n d phi by dt, okay. So here E is the EMF induced, phi is the flux, and n is the number of turns of the coil, okay. N is the number of turns of the coil. So this is the Faraday's law, which involves the flux linkage associated with the electrical parameter E, okay, and the mathematical expression that is given is this: n d phi by dt. E is the EMF induced, phi is the flux, and n is the number of turns of coil. So the EMF induced is directly proportional to the rate of change of flux with respect to time, okay, the derivative of flux with respect to time. So flux here is a time varying quantity, and here the number of turns of this coil also comes into play. So this is the first fundamental electromagnetic law. The second one is Maxwell's law. So we have already discussed about Fleming's rule, isn't it? We have already discussed about Fleming's rule, how Fleming's rule affects the uh, the, the direction of the force, the direction of the magnetic field, and the current. So here the magnetic field as a coupling medium, which comes into play in case of electromechanical conversion devices. So here Fleming's rule comes into play. We have already discussed about Fleming's rule, the Fleming's left hand, right hand rules I have discussed in the previous videos. You can check it out. So as per this Maxwell's law, it is in direct relationship with Fleming's rule. It states that when a current carrying conductor is placed in a uniform magnetic field at right angles, okay, when a current carrying conductor is placed in a uniform magnetic field at right angles, the right angles factor is very important. The conductor experiences a mechanical force, and the magnitude of that force is given by the mathematical expression F is equal to B into I into L. Here F is the magnitude of the force, B, capital B, is the magnetic flux density, I is the current flowing through the conductor, and L is the length of the conductor. Okay, so let us try to understand it. Let's say this metallic conductor of length L is placed in the magnetic field produced by the magnet. Now let's say a current I flows through the metallic conductor. The important fact to remember here is that the direction of the current, the direction of the magnetic flux, and the direction of the induced force, they are in mutually perpendicular direction. This is the same as that in Fleming's rule. It is also said in Fleming's rule. Now what the Fleming's rule says, it gives the behavior of a current carrying conductor placed in a magnetic field. It states that when a conductor is placed, a current carrying conductor is placed in a magnetic field, it experiences a force and tends to move, and the direction of the magnetic field, the direction of the force, the motion, and the direction of the current, they are in three mutually perpendicular directions, that is at 90-degree angles with respect to each other, just like if we want to imagine the x, y, and z axis. Same thing is stated here in Maxwell's law. Here it only gives the magnitude of the force which is induced. Only difference between Fleming's rule and Maxwell's law is that the Maxwell's law gives us a value, okay, and the expression of the induced force in terms of the parameters, in terms of current, the length of the conductor, and the magnetic flux density. So the magnitude of the force which is induced in the conductor is given by the expression B, product of the magnetic flux density, current, and the length of the conductor. So these are the two fundamental laws which govern the operation of the rotating electrical machines. First one is the Faraday's law, okay, which gives us the EMF, the magnitude of the EMF which is induced in a conductor or a coil, and which is placed in a fluctuating magnetic field, fluctuating flux. And the second one is the Maxwell's law, which is in direct relationship with Fleming's rule, and it gives us the magnitude of the force which is developed in a conductor when it is placed in a magnetic field. So you can say that the Faraday's law, okay, the Faraday's law is the output which is given in Faraday's law is EMF or voltage, okay. So this is the law which governs the operation of generators, okay, generators, the electrical machines, that is mechanical to electrical energy conversion, because here the expression gives us the value of EMF or voltage, which is an electrical parameter. In Maxwell's law, it gives us the expression for force, which is a mechanical quantity. So this Maxwell's law governs, dictates the operation of motors. What motors do, they convert electrical energy into mechanical energy, that is mechanical movement. So you can say the Faraday's law is about generators, Maxwell's law is about motors. But these things are very motors and generators, the construction and the operating principle is almost the same, only the input and output sides are interchanged. Okay, if we reverse a generator, we'll get a motor. If we reverse a motor, we'll get a generator. Okay, so these are the two fundamental laws that govern the operation of all rotating electrical machines, that is all types of motors and generators. The underlying, the basic principle is this, that is Faraday's law and Maxwell's law. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.